Chemical engineers are involved in some exciting problems to tackle the world's energy problems. And in developing countries, there's a need for electricity and cooking fuels. And there's a substance referred to as dimethyl ether, DME, that can be produced using a various feedstock of carbon sources such as methane or charcoal. And with it, we can generate electricity and cooking fuels. And it burns very cleanly, and it is a lot more environmentally friendly than just burning raw charcoal, for instance. And so what I'm going to do in this video is go through a chemical process design example that will give an overview of how a chemical engineer would approach a problem like this in practice. And so to begin with the problem statement, we know that in Rwanda there is a lake called Lake Kivu, and in Lake Kivu at a depth of 350 meters there is a source of methane and carbon dioxide that is dissolved in the water. And at these depths, what we see if we plot charts like these, we'll have the hydrostatic pressure on the x-axis, and we can have partial pressure of some component I on the y-axis. This is the hydrostatic pressure, which will be proportional to rho GH, and then it will also have certain vapor pressures for various component I's, like here. And so at a depth of 350 meters, we know that methane has a vapor pressure of 1.3 megapascals, and we're also given this concentration of methane in the liquid phase of 15 millimoles per liter. And we're also given that the vapor pressure of carbon dioxide is 0.3 megapascals, and it has a concentration of 80 millimoles per liter. And with this information, we want to figure out what purity and recovery can we get for extracting methane from this water if we use something referred to as a disengagement vessel. And that's what this thing is called, a disengagement vessel or tank. And the disengagement vessel will separate out the methane and carbon dioxide that has been dissolved in the lake water at 350 meters, put it into a gas phase. We can move that methane into a chemical reactor to produce dimethyl ether, and from there we can get the electricity and cooking oil that we need. And so before I jump into the details here on how to solve this, it is important to note, because we are dealing with very dilute systems here, you'll note 15 millimoles and 80 millimoles per liter are very dilute, Henry's law applies. And so Henry's law is very nice for us to use because it's dilute. We can assume it's a linear relationship. Let me try to write better. Between the partial pressure of some species and its concentration via some Henry's constant H sub I in that liquid phase C sub I. And so to take a step forward here, we're going to first look at the purity here. So this purity term refers to the concentration of the molar ratio of methane in the gas phase, which I shall denote YCH4, and that would be equivalent to NCH4 in the gas divided by NCH4 in the gas plus NCO2 in the gas. Because we're dealing with a two-component binary system here, this is what our denominator will look like in our molar fraction. And so our goal here is going to be, how do you actually start figuring what these terms are? And so one of the things you'll hear often in chemical engineering is we're going to set a basis, and what I'm going to call it is a control volume of 1 liter of lake water at 350 meters. And so if you were to dive down to 350 meters and take a balloon, and a 1 liter balloon that is stretchable, as you go up in pressure, because the hydrostatic pressure decreases as the weight of the water above it and all around it pushing in on the balloon is decreasing, that balloon's going to get bigger. You're going to develop a gas phase within that balloon. So just to kind of illustrate what's going on here, at z equals 350 meters, it's all liquid. But as we go to the surface, z equals 0 meters, our balloon will begin to have a gas phase as well as a liquid phase, and this is coming from the fact that we've got methane and carbon dioxide vaporizing into the gas phase due to the difference in pressure, or the change in pressure. And so in this case, with this 1 liter basis, I would like to begin to define how we can define what NCH4 is. And so NCH4 in the gas, we can think of intuitively as the number of moles of methane that have left the liquid phase and now exist, or that were initially in the liquid phase that have left it. And to write this out, what I will do is I'll say we can equate it to the volume of the liquid phase, V sub L, and we're going to multiply this by the concentration of methane naught, and this means the concentration of CH4 at Z equals 350 meters. And because we are interested in how much is left it, we'll have the same V sub L times the concentration of CH4 that exists at some new pressure, and I'll just simply call that CCH4. And just to underline this point, this is the moles of methane that have left the liquid phase. Because we only have 2 phases in our control volume, any methane that leaves the liquid phase must be in the gas phase following this relationship. Another important thing to note here is this Z equals 350 for this concentration CH4 naught. These V sub L's are the same because the liquid is incompressible. So as long as we are able to, because we're relying on a physical property of liquids, that they are incompressible, we can make this very nice statement, and we can even pull out the V sub L term and simply get CCH4 naught minus CCH4. And performing the same calculation, now analyzing methane that's in the, carbon dioxide that exists in the gas phase, we'll find the same thing where we can pull out V sub L because the liquid volume of our control volume is a constant 1 liter, and we'll have CCO2 at Z equals 350 minus CCO2 that exists at that whatever given new pressure. Now what you're going to note here is we don't know what concentration methane or carbon dioxide will have at that new pressure. So we've got 2 unknowns in this equation, and so we're going to need to write somehow 2 equations. And to do that, we're going to turn to Henry's law. But first, we're going to define Henry's constant, and we're going to go back to definition of Henry's constant so we can perform first on methane. Partial pressure of methane is equal to the Henry constant of methane times the concentration of methane. And we arrange this to solve for CCH4. And because we were given in our problem statement what concentration, the vapor pressure of methane as well as its concentration in the liquid phase was, we can evaluate what the Henry constant of methane will be by dividing the partial pressure of methane, in this case the vapor pressure, divided by the concentration of methane. And this was 1.3 megapascals, and it was 15 millimolar per liter. And this tells us what our Henry constant is. And I'd like to underline here, this is a constant value for all pressures. And so this will be very nice to know when we are generating our two equations to solve for our two unknowns, to actually evaluate what the purity and recovery are. And we will of course do the same constant calculation for CO2. So we've got P-vape CO2, which we were given at that particular depth, and we're going to divide it by the concentration at that depth, and we will have defined that constant as well. That will be useful to us. And we're going to now begin to build our two equations to solve for our two unknowns. So the first equation we're going to turn to tells us that P total times the mole fraction of methane will be equivalent to P total times, and we defined previously what YCH4 was. That was the number of moles of methane that exist in the gas phase divided by the total number of moles in the gas phase. So the moles of methane in the gas phase plus the moles of carbon dioxide in the gas phase. And as we were able to evaluate what NCH4 was above right here, and we were able to perform the same calculation there as well, we can now say that this is equal to P total times, I'm going to pull out the volume of the liquid phase. We're going to multiply this by concentration of CH4 at 350 meters, subtract it from concentration of methane, divide this term by VL, and we're going to take the denominator of this, and this will have CCH4 naught minus CCH4. We're going to add in the moles of the carbon dioxide, CCO2 naught minus, and sorry if we're going off the page, CCO2. And so now we will have fully defined what the left side of our equation is for Henry's law. And we know that the left-hand side of our equation in Henry's law is equal to the right-hand side, which is the Henry constant CH4 times the concentration of CH4. And so this whole thing is equation 1. And then for equation 2, we're going to perform the same calculation. Hopefully I can fit it on one line for carbon dioxide. So the total pressure times the mole fraction of carbon dioxide will be equivalent to, we're going to have P total times the volume of the liquid phase we're working with times, and then concentration of carbon dioxide that existed at 350 minus concentration of carbon dioxide at the new pressure, divided by, we're going to again divide by VL, and you'll note here how these control volumes that we went with canceled out, which is very nice. And we're going to divide this by the total number of moles that exist in our gas phase, which is equivalent to the total number of moles that have left the gas phase. CCO2 naught minus CCO2, and this is equal to HCO2 times CCO2. And so if you look here, we've got the unknowns, two unknowns, CCO2 and CCH4 appearing in two equations. and we know we're given P total, we're given these initial conditions, and we can solve for these two unknowns using MATLAB. I will leave that to you guys to do, or you can also do it by hand or Excel, but it is a pretty straightforward calculation. And this wraps up how we can use Henry's law in our process design to evaluate. And I should probably get to how we're going to get the actual recovery stuff. So now that you know what CCH4 and CCO2 are, recovery, sorry about that, recovery is simply defined to be the number of moles of methane that exist in the gas phase divided by the number of moles of methane that existed in our control volume I shall call NCH4 naught. And this should make intuitive sense. If we're able to extract all of the methane from our initial control volume, then we'll have 100% recovery. If we're not able to get anything, it'll be 0. And then in terms of purity, as we defined earlier, was simply equal to the mole fraction of methane that exists in the gas phase, and I call that Y sub CH4. And so this wraps up how we're able to use Henry's law in our analysis of the purity and recovery that can be obtained at a given total pressure. And we're applying this to a real-world situation that can really help people out. So it is very exciting stuff. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.